Hello everyone, we are at the topic of transistor amplifiers, and today we're going to learn about their characterization and different configurations of these transistor amplifiers. Let's start with the characterization of transistor amplifiers. At the beginning of this course, we talked about how dividing the circuit into building blocks can be used to simplify the analysis and design of the complicated circuits. A typical analog circuit consists of a load and a source that are two-terminal devices and several two-port networks. Here, we would like to characterize the transistor amplifiers as building blocks of analog circuits. Since BJT and MOSFET devices are voltage amplifiers, we are going to use the well-defined voltage amplifier model to characterize them and use them as building blocks in analog circuits. This is the voltage amplifier model. Its parameters are Ri, or input resistance. It's defined as Vi over Ii. This is the current that flows into the amplifier. And R sub O, or the output resistance of the amplifier, is defined as negative of V out over I out when Vi is equal to 0. And the open loop voltage gain, or this AVO, and it's equal to V out over Vi when there is no load resistor or when you have open loop for your amplifier circuit. We have two other gain definitions or gain equations for the amplifier circuits. One of them is voltage gain of the amplifier, or A sub V, which is equal to V out over Vi. This equation takes into account the effect of load resistance if there is a load resistor connected to the amplifier circuit, and the voltage gain of the circuit, which we are going to show with A, and that's equal to V out over V signal. So this V out over V signal, that takes into account the effect of output resistance of the V signal if the signal source has an output resistance. The voltage gain of the circuit, or the overall voltage gain in the amplifier circuit, including the load resistor and the output resistance of the signal source, is V out over V signal, which mathematically we can write as Vi over V signal multiplied by V out over Vi. So these two cancel out and the result is Vi out over V signal. The benefit is that we can write Vi over V signal using the voltage divider network in here. We can write it as Ri divided by Ri plus R signal, and we know that V out over Vi is equal to A sub V, or the voltage gain of the amplifier itself. If you look at the equation of Vi over V signal, in this equation, for Ri values much greater than V signal, Vi is going to be almost equal to V signal. When Ri, or the input resistance of the amplifier, is equal to R signal, Vi is going to be half of the voltage from the signal. And for Ri values much smaller than R signal, Vi is going to be equal to 0. As a result, we prefer large Ri values, or we prefer the voltage amplifiers with large input resistances. Now, if you look at the expression of V out over Vi, you can see that for R out values much smaller than R load, the voltage gain of the amplifier is going to almost be equal to open loop voltage gain. For R out equal to RL, the gain of the amplifier is going to be half of the open loop voltage gain, and for R out values much greater than RL, the gain is going to be equal to 0. So we prefer voltage amplifiers with smaller output resistances. Let's take a look at the entire process of analyzing amplifier circuits. The circuit inside the red box shows the total amplifier circuit, including the signal voltage and the load resistance. The circuit in the blue box on the right shows the bias circuit for the amplifier circuit in the red box. For drawing the bias circuit, we zeroed out the signal source and opened the capacitors. The circuit in the blue box on the left is the signal equivalent circuit for the total amplifier circuit. We replaced the MOSFET with its small signal model, shorted the capacitors, and zeroed out the independent voltage sources. Because the parameters of the small signal circuit depend on the DC values of the entire amplifier circuit, we need to solve the bias circuit first, calculate ID and VDS values, and from there we can find the value of GM and R sub O in the signal equivalent circuit. If I characterize my MOSFET amplifier by finding its output resistance, input resistance, and open loop voltage gain, then I can take this entire circuit and replace it with the elements inside this box that are input resistance, output resistance of the amplifier, and the open loop voltage gain of the amplifier. That way, for different load resistance values or different signal sources with different output resistances, I don't need to solve the amplifier circuit on the left several times. After characterizing it, I know everything about my amplifier circuit, and I can solve this circuit instead for different RL values or different R signal values. This is going to simplify the calculations, especially if you have more than one stage BJT or MOSFET amplifiers. Here is an example of how the characterization of amplifiers can be used in solving multiple stage amplifiers or cascade of amplifiers. In this circuit, we have two stage amplifiers. That means there are two MOSFET amplifiers that are connected in series. So you have stage 1 and you have the second stage here. Our load is connected to the output of the second stage, and V signal with its output resistance are connected to the input of the first stage. If we characterize the amplifier in each stage by replacing it with its voltage amplifier model, that means finding R sub I1, R sub O1, and AVO of 1 and VI1, and this is VI1. Then the second one, for the second one, we have RI sub 2, A sub VO2 and VI2, and we have VO2, and this is VI2. Then finding the overall gain of this amplifier circuit is going to be much simpler than solving the top circuit and finding V out over V signal. So this box, the second box, belongs to the amplifier parameters of the second stage. So this entire circuit, the first box, this one, belongs to the amplifier parameters of the amplifier circuit in the first stage. So this R sub I, for example, this is this R in, this R sub O, this is this RO1, and so on and so forth. V out over V signal, this V out over this V signal equals to the same thing as here, V out over V signal, but from the bottom circuit we can write V out over V signal equals to V out over VI2 multiplied by VI2 divided by VI1 multiplied by VI1 divided by V signal. And each one of them I can find using the voltage divider network that I can see in the bottom circuit. Here is the process of solving transistor amplifier circuits. We're going to draw the bias circuit, find the bias point or find the DC values of the circuit, find the small signal parameters GM, RO, and RPi for the transistor circuit, draw the signal equivalent circuit, find the amplifier parameters RI, RO, and AVO, and use the voltage amplifier model and the calculated parameters to find the amplifier circuit gain. Let's look at the transistor amplifier configurations. There are three possible BJT amplifier configurations that are common collector or emitter follower, common emitter, and common base configuration. Common emitter configuration can be modified to common emitter with an emitter resistor configuration. We are going to study each one of these configurations other than the common base amplifier, which we are not going to cover in EC65. In a BJT common collector or emitter follower configuration, whether it's built with an NPN BJT or a PNP BJT, the input is applied at the base and the output is taken at the emitter. If you look at both of these circuits, the input signal or V signal is applied to the base and the output is taken at the emitter. So this is V out here, V out taken from the emitter, and the input is applied to the base of the transistor. Here are some examples of common collector or emitter follower BJT amplifier circuits. The top circuit is only the signal circuit, but the bottom ones show the entire amplifier circuit, including the bias and signal. So all three circuits are in common collector or emitter follower configuration because the signal is applied to the base and the output is taken from the emitter in all of these circuits. Their bias configuration is different from one another. In a common emitter configuration, the input is applied at the base and the output is taken at the collector. If you look at these two circuits, the input is applied to the base of the BJT and the output is taken from the collector node of the amplifier. In the circuit on the right, there is a resistor connected to the emitter of the BJT amplifier, but it is used only for bias circuit. In the signal circuit, because the capacitor is short, that capacitor is going to short the RE. So in terms of signal circuit, both of these circuits are equivalent. Common emitter with an emitter resistor configuration is the modified version of the common emitter amplifier configuration. Just like the common emitter configuration, in the common emitter with an emitter resistor configuration, the input is applied at the base and the output is taken at the collector. The third configuration for the BJT amplifier circuit is the common base configuration, in which the signal voltage is applied to the emitter of the transistor and the output is taken from the collector. For the MOSFET-based amplifiers, there are three configurations: common drain or source follower, common source, and common gate. There's also a modified version of the common source configuration, that is common source with the source resistor. Let's see how they look like. In the common drain or source follower configuration, the input is applied at the gate and the output is taken at the source. Just like BJT transistors, we can build this configuration with NMOS transistors or PMOS transistors. We can build all of these MOSFET amplifier configurations with NMOS transistors or PMOS transistors. The same goes for the BJT transistors. Here are some circuit examples that are in common drain or source follower configurations. The circuit on the top is only the signal circuit. In other words, the bias components are removed from the circuit. The bottom ones are the total amplifier circuits that contain both the bias and the signal components, and the difference between them is the bias configuration. All of them are in common drain configuration because the signal is applied to the gate and the output is taken from the source in each one of these amplifier circuits. This is a PMOS based amplifier, this is NMOS based, and this is an NMOS amplifier circuit. In the common source configuration, the input is applied at the gate, but the output is taken from the drain. In both of these circuits, the input or V signal is applied at the gate and the output is taken from the drain through this capacitor. In the circuit on the right, a source resistor is used for the purpose of the biasing, but because there is a capacitor in parallel with that resistor, in the circuit analysis, we're going to replace that capacitor with the short circuit. So in the signal circuit, RS is going to be shorted. As a result, these two circuits are similar in terms of their signal circuits. The modified version of the common source configuration is the common source with a source resistor configuration. In this configuration, the input is applied to the gate and the output is taken at the drain, just like the common source configuration. But there is a source resistor connected to the source of the amplifier and it is not bypassed by the capacitor, so RS is going to be present in the signal circuit. The last configuration for the MOS amplifier is the common gate configuration, in which the input signal is applied at the source and the output is taken at the drain. In summary, in today's lecture, we learned how to characterize BJT and MOSFET amplifiers, and we learned about different configurations of MOSFET and BJT amplifiers. In the upcoming lectures, we are going to learn about how to find RI, RO, and AVO for each one of these configurations, and how to find the response of these amplifier circuits for different R load values and signal sources with different R signal values.